Welcome to Cassandra Lunch number 140. Don't forget to like and subscribe, as well as turn on the notification bell so that you can get notified every time we post a video or go live. In today's talk, Obioma Anomnachi compares our fine-tuned Llama 2 model to Retrieval Augmented Generation with base Llama 2. We evaluate using some great industry standard statistical measures. The co-organizers for this event are Rahul and myself. And if you are interested in becoming a co-organizer, helping us find a speaker, or reaching out to people in the Cassandra community around the world, you can drop me an email or an email to this marketing email. If you yourself are interested in giving a Cassandra Lunch or giving a talk at our sister lunch, Data Engineers Lunch, please reach out to me. We are part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. Data Community DC is actually made up of a lot of different groups, generally centered around data, and you can find out more about all the groups at datacommunitydc.org. At Cassandra Lunch, we cover everything that speaks to, talks with, and is Cassandra. Cassandra variants, Cassandra add-ons, Cassandra extensions. And today we're going to be showing you a cool way that we're using Cassandra in AI. If there's anybody new that would like to say hi, what brought you here, please drop something in the chat. Don't forget to like and subscribe, as well as turn on the notification bell. A few rules. If you have a question, please ask it. Be polite and courteous to others, and share what you know with us. We'll handle questions in the YouTube chat. I will ask them to Obi close to when I notice them so that they can be addressed at the best possible time. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. Cassandra is our bread and butter. We also are working in the generative AI LLM space and are really excited to share our practice with you. Thanks to all of our sponsors, including DataStax, George Washington University, all of our institutional and organizational sponsors, and of course, our customers who make this all possible. If anyone has any job offers, you're looking for a job, please drop links in the chat. If anybody has any meetups, hackathons, classes, or conferences that you would like to promote, feel free to drop those links as well. We currently host Cassandra Lunch every Thursday at noon Eastern. Our sister lunch, Data Engineers Lunch, takes place Mondays at noon Eastern. All of our videos are available on YouTube, starting with the Cassandra Lunch number 10 on the Cassandra Lunch playlist. You can also find this talk and the previous 3 talks in this series on our No Code and Generative AI playlist. I'd also like to highlight Cassandra.link, a hand-curated site with resources for Cassandra. We curate this site, and everything here is vouched for and interesting. Also, check out our runbooks. Our most recent Cassandra runbook is number 17, and it is posted at anant.us/runbook. With that, I would like to thank Obi for being here, and I'm passing it to you so you can get started.
All right, thanks, Nick. As you heard, my name is Obioma Anomnachi. I'm giving a presentation today. This is probably the last part of our fine-tuning with QLoRA discussion. Today we're talking about evaluation. Oh, wait, 1 second. Turn the AC off, hopefully increase the audio quality. So today we're talking about evaluation versus RAG. So we mentioned RAG previously in these talks, but I don't think we've discussed it elsewhere on Cassandra or Data Engineers Lunch. It's basically a separate method for improving the performance of your LLM on particular queries. And we're going to compare that to the fine tuning that we just did and how that affected our model. So getting started. What is RAG? So RAG stands for Retrieval Augmented Generation. It's a sort of hybrid natural language processing approach that isn't just the component parts of retrieval or generation, combines those two together. And hopefully you can use it to create more comprehensive and contextually accurate outputs from your models. It leverages external data sources, including knowledge corpora, corpuses, however you pluralize that, or databases, or web searches, or other methods of retrieving external knowledge, and then uses that to augment the generative capabilities of language models. So, like I said, retrieval augmented generation, there's a retrieval stage, there's a generation stage. The retrieval stage, the model retrieves information from a pre-existing corpus or knowledge base, so something that already exists and you have ensured is filled with relevant or useful knowledge. And the generation stage uses a generator, like an LLM, and provides it with that extra context along with whatever user prompts or system prompts or whatever make up the rest of that system, and then generates results using all of that information together. RAG is effective for complex tasks that require in-depth knowledge, specifically if that knowledge has to be factual and domain specific. So a comparison to traditional large language models. Large language models depend on the data that is in their original training corpuses. We talked these last few times about how you can extend that via fine-tuning, training them on new data, but once that training process is complete, then they're relying on their original training data plus whatever modifications have been made to the model weights because of your fine-tuning data. They do text generation based on learned patterns. They struggle with tasks requiring up-to-date information, like it was said. They rely on the data they were trained on, but that's even for things like sentence structure. So struggling with up-to-date information has to do with both that they don't have access to any information newer than the data that they were trained on, and also potential hallucinations that they can, because of the probabilistic nature of the models, they can fail to provide factual information. They can provide false information, misleading information, etc. And they lack specific factual knowledge that's not present in the training data. But like I said, they can also give factually false answers, even if the correct answer theoretically could be found somewhere in their training corpus. RAG models, they have their generative component, yes, with an enhanced process based on information retrieval. The information retrieval is dynamic, so based on the user prompt or based on updates to the data, you can change what data comes out of the retrieval step, and then you get improved performance, especially on tasks requiring detailed or domain-specific information, as long as your retrieval step accurately provides that information. So here's a diagram of a RAG. So in order, prompt and query come in. So prompt is stuff like system prompt, or if you have built a system on top of an LLM that defines part of a user prompt, and then the user query itself entered by the user, those come in. The query then goes out to your retrieval system, where there is some sort of mechanism for searching for related knowledge. We'll cover the possibilities for that in more detail a little bit later, but the query goes out to your knowledge sources, particularly, so those knowledge sources are then filtered down and relevant knowledge comes back. And then the prompt, so all of your system prompt stuff, everything that is the definition of what you're doing, the user query, the specific things that the user wants, and the context all go out to the large language model together in some format defined by defining your RAG system. The large language model gives back generated text. So comparatively, if you were using a normal LLM process, prompt and query come in, prompt and query go out to the language model, generated text comes back. There's no retrieval step. So talking about retrievers. So they're connected out to external knowledge sources, external corpuses, corpora. So things like databases, document stores, PDFs, books, etc. Domain-specific databases. So if you have, say, we did here at Anat a RAG project on scientific papers. That's a domain-specific database. You can dig deeper into those for more specific domains, but then also fields like medical, legal practice, etc., will all have their own databases filled with domain-specific knowledge, where certain words mean certain things in this context and not in other contexts, so that the generalized knowledge that is sort of available to LLMs won't be able to accurately represent it. And then they can also have access to real-time data, whether that's a database that is continuously being updated or live sources such as news feeds or web search, data that can change between the times that you query it. And in fact, you expect it to. And then the search mechanisms themselves. So you have all of this data in a big block. How do you pick out data that's relevant to the query that the user has submitted? That's what these search mechanisms are all about. So dense vector representations are all about, so neural networks use embeddings of text into numerical representations, and that embedded text, the embedding space of that text, we'll discuss it a little bit more later, but the embedding space of that text is meaningful in that the location in your whatever dimensional space is representative of the meaning of that text, so that similar texts get embedded closer to each other and dissimilar texts get embedded farther from each other. And then there are sparse vector representations like TF, IDF, and BM25, which are, if you remember when we talked last time in our evaluation methods talk about how you can do human eval or benchmarks, or you can do statistical measures. And there are these more sophisticated ways. So dense vector representations are sort of this more sophisticated way where everything is about where these particular meanings have been placed in a high dimensional vector space. Sparse vector representations use sort of counting methods to sort of approach the same idea. So TF, IDF has to do with basically how many times particular words in the query appear in the document versus how many times they appear in your corpus in general. So it's, I forget the acronym, but the second one is sort of inverse. So it's the first part, TF, is about how often the word appears in the document, the specific document that you're talking about. And then the IDF is about how much it appears in the document, and it has a sort of inverse relationship to the final value. So that words that show up a lot in this document but don't show up a lot in the sort of in all your documents are highly rated, get high numbers attached to them. And then numbers that are in this document a lot but show up in all documents like the and are going to get low numerical ratings. And then for words that that don't show up in this document, so words that are relevant to the query that don't show up in this document but do show up in your data set at large will get you low numbers again. And then words that don't show up in this document but don't show up in the document in general will again get you lower numbers. And then hybrid techniques combine those dense and sparse vector representations for more accurate retrieval. And there are things like relevance scoring and filtering and ranking, which more traditional like search indices and things like that use in order to determine what's relevant. So embeddings and how they relate to similarity search. So we're talking specifically about the dense vector representations from the last slide, because that's what we use in our RAG. So what are neural embeddings? Neural embeddings are dense vector representations of words, phrases, sentences, or documents. So different embedding models can work different ways. Sometimes you embed a single word. Sometimes you embed a phrase. Sometimes you embed specifically sentences or paragraphs or whatever and sometimes the length of the text does not matter. You can embed anywhere from up to a single word to some limit that the model can understand, and it will generally truncate whatever comes after. Or you can do one where you embed entire documents. Basically, I talked about a vector space and embedding space earlier. So it sort of works the same way as like on a normal two-dimensional graph. If you wanted to plot a city from above, every point on that map would have an X and a Y value. Things that are farther apart in space would have bigger differences in their X and Y values. They'd be farther apart on the map, and things that are closer together in real life would be closer together on the map. In this case, you end up with, if you look at the bottom here, dense vector embeddings, they have fixed dimensions, but they're typically very high dimensional. So 300 dimensions, 786 dimensions, 1,536 dimensions. In these high dimensional spaces, locations along the different axes. So in our two-dimensional graph example, the x-axis represents horizontal space, the y-axis represents vertical space. In these high dimensional spaces, each direction will sort of be associated with a meaning. And so the placement of a particular embedding, so that's some snippet of text, in that large dimensional space, things with similar meanings are closer together to each other, things with different meanings are farther apart from each other. And that's what we're going to use because we can calculate distance between 2 points no matter how many dimensions this space has. Use that to get documents that are similar to the query created by the user. And that's called similarity search. There are different ways to calculate distance in high dimensional spaces, but that's not part of the scope of this presentation. Okay, so what are the advantages of using RAG?
So,
In this
Obi,
case,
can we go back to those last two slides? I'd love to ask a question or two. So, when we look at these search mechanisms, how do they sort of compare in like cost and effectiveness?
Okay, so that's an interesting question. Dense vector representations these days are actually a lot easier than they used to be. So
is
if
this
you
like
remember,
similarity search?
yes, so dense vector representations are specifically the embedding models that are associated with LLMs. And because LLMs have proliferated so much, a lot of these different models are available and they are very high quality. So in the past, it would be much harder to use dense vector representations because you would have to build up a model associated with an embedding space by putting in a bunch of words and defining where they lay, and basically you'd have to build your own embedding space, which would be hugely costly. But now you can just get
go ahead, sorry.
Now you can just get access to the OpenAI embedding API or any number of other embedding APIs, and they will give you back a dense vector representation that's usable for less than a cent.
So what essentially this means for Astra is you send the embedding call to OpenAI, you embed the response in your database Astra, in your Astra database, and then you can just do similarity search on that table that has your embeddings.
Yes.
Okay, great.
And then a sparse vector representation, if you wanted to build one, you could use a pre-made one like before, but because neural vector representations are so easy to get these days, people aren't really building these out anymore. But basically, you take a big corpus of data, and then you define all of these against your query for every document in the data set. So somewhat costly, but not as much as building out a whole embedding model would be. And then hybrid techniques, of course, you need one of each, et cetera, et cetera. Relevant scoring and filtering and ranking are stuff that search indices would use. If you put your code into like Elasticsearch, you could set that up to use filtering and ranking and stuff like that.
So are you doing the ranking on the embedded vectors, or are you doing your relevance ranking based on the
So
pre-embedded queries?
yeah, if you're doing relevance scoring or filtering and ranking, under the hood, those will still use numerical representations a lot of the time.
Yeah.
But as like a person interacting with Elasticsearch, you're not going to, see any of what's going on under the hood. You're going to put in your search query. It's going to say this document, this document, this document, and give each of them a ranking.
Okay, cool.
And there are many different types of ways to do search. So relevant sorting and filtering and ranking can include stuff like Google PageRank. Like if you just put your query into Google and give back the first result, that's a retriever.
Yeah.
But a lot of these are based on what words are in your query. How does it relate to what words are in the documents? But ultimately, that's mediated a bunch of different ways.
Um, so with these neural embeddings, this is when we're talking about neural embeddings, how is this different from using the OpenAI embedding API?
Those are the same. So when we're talking
Okay,
about neural embeddings or dense vector representations, those are the same as the OpenAI embedding API.
great. Thank you. Just wanted to clarify that.
Yeah, great. Okay. So what are the advantages of using RAG, at least over a normal LLM? It incorporates external knowledge, stuff that isn't in the training set, but it can also be used to ensure factuality. If you are sure that the information in your data set is accurate, and you can make the LLM use that to answer questions or user queries rather than relying on the probabilistic nature and whatever was in the original training data set, you can reduce the risk of getting incorrect or outdated information. And then answers given by a RAG system should be more relevant to things that are happening. So more relevant to the user query, more relevant to current events, more relevant to domain-specific expertise, as long as those things are included in your RAG dataset, inside your retrievers database, essentially. And then you can use these for various tasks. It can adapt based on the user query. So if you set up a person with a retriever system, they could get relevant documents, and that would be useful. You could do things like search documents, search for specific scientific articles about specific topics, get a document that helps you answer a question, but the generation side means that you can use it for all these various contexts. It's the same system, but if you put in a question, it can answer it. If you ask for a summarization of a topic, it can theoretically do that. And it can converse back and forth with you in a conversational style.
So, on the topic of RAG, how
Yes.
much impact does the way that you index your data have?
It has a decent amount. We'll actually see later that there are lots of things that can impact your RAG performance. Like you can't just implement whatever you want and get a return.
Yeah.
It depends on what is your base model, what is your method for putting information, combining information into a prompt. What is the data in your database actually like? All these things can have an effect
Mhm.
on the quality of answers that you're going to get out of a RAG system.
So, for example, just like assuming that you can take a book or a series of papers, like the example we did with the science papers, and you can just chop them up into equal size bits and index or embed those bits and index them sort of with a flat model, you're not going to get the best retrieval results
Uh-huh.
from, yeah.
Yeah. So this is where things like there's a concept called semantic chunking.
Mm-hmm.
All of these things have an effect on your RAG your retriever in the end. But semantic chunking is basically breaking up your snippets of text along, boundaries of meaning. So when
Mhm.
topics switch or something like that, that's where you cut. But even just like, let's go for a very, very like simple, understandable example. You have an embedding generator that, like the smallest ones available these days, will truncate your text after a certain amount of time. So it says, I can take 512 tokens of text at one time. And after that, anything that comes out is not going to be reflected in the embedding. And you chunk your data such that it's 1024 tokens or however much. Half of everything you have decided to chunk has been thrown out in terms of finding relevant documents. So
Yeah.
you can end up in a situation where the user queries for something, but it's in one of those cutoff sections. So the relevant documents aren't actually being pulled in by the retriever.
Great. Thank you for that example. Yeah.
Yeah. So yeah, there are absolutely situations where you can set up your retriever or your embeddings in ways that have effects on your final RAG product. All right, so comparing RAG to fine tuning. So RAG, you get increased accuracy and relevance, up-to-date information, domain-specific information, dynamically updated information. So if an article is edited and has another version come out that's more relevant, your retriever might be able to pull that instead. Scalability and flexibility, you don't have to retrain your model to get new performance. You can just put different data in the database. The knowledge base is easy to update with new information or new domains. You might, in that case, need to update your retriever as well so that it's not, say, pulling in medical text when you're asking legal questions. You might need some way to differentiate what documents are in fact valid for a particular query. And it's more cost efficient. You don't need a huge data set. You only need the relevant information that your users are going to query. In the case of fine tuning, to even have an effect on the weights in the model, like to have a significant effect on those numerical values, you need a certain amount of data. And then it can utilize existing knowledge sources instead of having to put them together in a data set yourself. When you're fine tuning, you get to customize and specialize more. Like I said, the specialization that happens in fine tuning is more about the manner of language that you're using, how it responds to particular prompts, rather than what specific data is being pulled in to answer specific questions. And you get highly specialized models out, or at least more specialized than the general LLM that they're pre-trained. Um, Improve performance on specific tasks. So, like I said, it's for specific tasks how the LLM is going to respond to specific types of language. And if you have specialized requirements, the way that your LLM, in the way that your LLM responds, rather than a conversational output, it might be possible to fine tune your LLM to produce reports specifically, even when asked questions that might otherwise just result in, a piece of text written in a conversational manner. And you get more control over your output that can help you improve accuracy and reduce errors. It doesn't ensure factuality, but these adjustments to the model can help reduce errors. And you get more control over the style of the generated content. And then evaluation. So that's what we're here to do today, but we already talked about it last time. The answer is ultimately generated by an LLM. In fact, it's Llama 2, the one that we fine-tuned. And you can evaluate the outcomes the same way, because that's really what we were set up to evaluate last time. We were evaluating the performance of the LLM before it was fine-tuned to the performance of the LLM after it was fine-tuned. And because the LLM is still producing answers here, you can understand them the same way. And like I said, performance depends on the sophistication of the retriever mechanism. the capabilities of the LLM and the quality of the data all at once. Okay, we're gonna move on to the demo. Any questions before we do that?
They've all been addressed so far.
Okay, great. So, first thing to talk about, what data do we have? How do we turn that into a retriever that can be used here? So the data that we started off with, last time, what we did with it was we generated a set of training data for an LLM from these documents that we have, our Cassandra link archives, essentially. And the way that these were stored, because of limitations in Astra, is that this content field, it contains all the article text broken up into, I think, I forget exactly how long, 8,000 character snippets or something like that. So it's just pure article text. Some of these are even, the scraper picked up that this is embedded content. I don't know what's on this page here, because the page is just an embedded YouTube video or something like that. So there's no actual article to put in here. What we did last time was we turned that into instructions. So we got the document. It says explain the modifications, et cetera, et cetera. It asks a question or gives an instruction to the model. It turns the article into some, text snippet of input. So this could be said to be sort of a retriever, except that it was done by GPT-4 or GPT 3.5. What it did was it took the article, it said, this portion is relevant. I'm going to rephrase it as a snippet of text, and I'm going to put it in here to be the data to fine tune the model on. So it picked out a specific part of the article, summarized it, and put it in the model here. And then it also generated an output, an answer to the question or something following the instruction. And that was used to fine tune the data. So what we did from there, going back where we have just our articles cut up into snippets, we needed to turn that into a RAG database. And Astra has a vector search type of table available where you insert your text, you insert your vector. Remember, vectors are fixed lengths, so the table has that value as the length for vector objects. Okay, so we get our content, which is, the snippet of the article that's relevant, the article ID from the main table, the ID in this table, and then the vector. So if we were to look at a vector, oops, not that. We were to look at a vector, what we're seeing is, 1,000 values that range from -1 to 1. And so, unit lengths along how far for each of these potentially meanings embedded in the data set. We're just looking at generate RAG database. So the process for turning these snippets into embedded into embeddings and storing them in the DataStax table for your retrieval. So the DataStax vector table also gives a vector, also provides vector search functionality. So the vectors and the content are stored in the article. You provide another vector. It has to be of the same length. So, and generally, okay, it has to be the same length and it has to be embedded by the same embedder. Otherwise, the meanings are going to get twisted. So even if two embedding models output the same length of vector, that's not a guarantee that vectors used by the one are going to be compatible with vectors used by the other. So what we do here, we set up our token endpoint for access to Astra, our in collection and our out collection. We create the two DBs here. How many articles are we processing? And then here is the actual code that does the embeddings. Client, that's the OpenAI client that we defined earlier. Embeddings.create. Input is the snippet text. Model is text embedding ADA 002. And then we pull out data 0, the first result. We only handed it one thing, so there's only one result to actually look at, and then dot embedding. And that gets us our vector, which we then insert into the Astra database with the specific column name $vector. That's the special vector column in DataStax Astra. Each vector table has exactly one vector column. You cannot store you can store multiple vector embeddings for one piece of text in one table if you store them as arrays, but you can only do vector search on the vector column. We store it alongside its content. This is important because when you perform vector search, DataStax actually gives you back the whole row, and you need some way to associate the embedding that's in that table necessarily to what it was embedded from. And then we put it alongside the article ID, and then if you were paying attention, you might have noticed this last column here, chunk index. So these articles can be longer than one chunk. So if they are, chunks are embedded with their indices. So if an article is broken up into 4 chunks, they will have the same article ID, but chunk 0, 1, 2, 3.
So can we spend a minute looking through this sort of table definition you've made for this is your RAG table, right?
Yes.
So we have the content, we have the ID. If you were trying to go one step further and make this a little more valuable, would it make sense to add something around like context or topics or like keywords that another column that you could use for sort of further refinement of this table?
Potentially, but I think once we have our text embedded, we mostly
Mhm.
want to let the embeddings handle determining which articles are relevant. So it's definitely
Yeah,
possible, but these are all documents from a single context. They're all
yeah.
Cassandra link articles. If we had more varied stuff that
Mhm.
we were putting in this table, I would definitely want to put in tags or some other method of cutting down which documents are even relevant for a particular query.
Yeah.
Or, you could just split them up into different tables at that point and,
Okay. Okay,
um,
thank you. Yeah.
let that do
So
it.
it's really the volume of the number of vectors that have to get searched through. That's the really important thing here, right? In order to continue to get decent results, we can't have a huge vector space that we're searching through.
Yes, basically. If you end up with a bunch of very similar embedded
Mhm.
articles, then telling the difference between which ones are more or less relevant for a user query is going to get harder because there'll be smaller differences between them. And then also just having to generate, a rank in terms of similarity for every object in the data set. The difficulty for that goes up with how many dimensions your embedding has,
Mhm.
but just the computational requirement of doing it for all of the rows in the data set. Um, it's definitely easier than, some other NLP methods because it's just, you have these two sets of numbers, you do some math, you get out the distance between them. It's relatively easy. The bulk of the work here has been done in making the embedding model. Um, so actually calculating the similarity between two embedded pieces of data isn't that difficult.
Okay. Great, thank you.
So that is how we generate our RAG data set. You cut up the text, you get the text embedding from whatever model, and then you put it into the data set along with the rest of the relevant data. So the next question is, how did we then get responses out of that? So this is Colab. Again, we're using Colab rather than Gitpod here because this particular step needs enough resources to load in the model weights to use the Llama 2 model. This is just the base Llama 2 model, not the fine-tuned one. But this is essentially the same method that we used for getting the results of our fine-tuned model earlier. So what this does is it loads in data. The build instruction prompt method is different here because it uses this get similar snippets, which pulls the bits of context out of the table. So the user provides their instruction and context. So we take the instruction from the table and we take the original context that was generated by GPT in our first talk, and we use that to find a particular article that is relevant to those two pieces of text together. We pull out that article. In this case, we pull out the first 3 articles that come out according to the similarity search, which is vector.find. We provide the embedding, we provide how many responses we want, we get back our relevant rows. And then we pull the content out of those rows, and then we put them into the larger prompt that's generated for giving to the LLM. So all right, so what we see here that was provided, so our full prompt is generated out of start, question, response, extra context, answer. So start is just a general system prompt, read the instruction below and provide an answer. The instruction comes next, that's the actual question that's being answered or instruction that's being followed. The original context from the database generated from the article. Sometimes this is commented out. The extra context, which is pulled from the RAG table, the retriever, and then a prompt for a response. And then we combine all these together and we get a response. So this is where you can see something crucial. We've sent this to the LLM, and the response that we've gotten, the original, so this is the prompt, and the response from our LLM was, I recognize these formatting cues, let me just put them all in a row. Because, as we established last time, base Llama 2 is not instruction fine-tuned. What it wants to do when provided with a prompt is generate more text that follows that same prompt. It tries less to understand the instructions given by the user than it does to follow on in an appropriate context to the document that was provided. And we'll see this same response when we look at what our RAG responses look like, because if the base Llama 2 model doesn't know to follow instructions, it just knows to continue the format. And we've provided even more format in the appropriate, we provided even more document in the same format, it's going to be even more likely. So we'll actually see that we ended up with worse than the original response in terms of answering the question that was provided. And that's why instruction fine-tuning, generalized instruction fine-tuning, can be important, even if specific like domain level fine tuning isn't done. So the potential reason to use an instruction tuned model like Llama 2 instruct, GPT 3.5 instruct, etc., over their pre-trained counterparts that are just more generalized. So if we go and we look at some of these, so our instruction, our input, our output, and then the text that is combined all of those things together and prompts for response. And if we go back here to look at the test instructions. So this database was originally used for the prompts that it was not fine-tuned on so that it could be tested on. We leave out some of the data set to test on. It's not part of the fine-tuning data set. It's not part of the data that was put into the RAG retriever. This is more examples that were trained from more articles that are not part of either of those training data sets. You can see we still have our original response, our fine-tuned response, and what came back from the LLM in those cases. So you can see that fine-tuning, so in the original LLM, we get a bunch of these type of answers where the formatting of the prompt is continued on, but it's not necessarily answering the question here. It's just repeating other information from other places, stuff that it knows about Spark, links that it has somewhere in it from either the fine tuning or the original training, or just nothing. It just formatting. Whereas the fine-tuned LLM knew very well that when someone says, how do I set up a Cassandra database using DataStax Astra for et cetera, that it's asking you to come up with a method for doing that, set of instructions that will allow you to do that. And that's because those types of answers were reflected in the GPT generated outputs that were used as a basis for the fine tuning. And then if we scroll all the way to the right, we'll see that the RAG LLM responses are even worse in this regard. So we've muddled up the format and we've added even more like cues, sections, things like that, such that when the LLM is theoretically tasked with responding to an instruction, what it does is it finds a pattern in the document and then it repeats it. So a lot of these are the same as the question asked in the response, or they are repeated. We provided extra context. So it sees context, it sees extra context. You follow up extra context because we have 3 pieces of extra context from the RAG table. It assumes that everything that comes next should be more context, more section headings, more context, et cetera, et cetera. And so very few of these have actually generated a response that is in human terms evaluable. So if we did human evaluation on this, we would end up with a whole bunch of zeros. This isn't even an attempt to follow the instruction or answer the question. The LLM, I think, is a bit more generous. You can see some of these results, I think, over here are pretty high, even though a human looking at them would say, this doesn't really answer my question. Some of these are good, they're okay. But this is an example of how sort of in the name of fairness, what we did is we used the same prompt structure, we used the same, everything. We used the same model, we used the same to try and get, an evaluation that makes sense. The context of this is Llama 2 fine-tuned, this is Llama 2 not fine-tuned with RAG. Those comparisons seem to make sense, but Llama 2 can't actually do instruction following by itself. So it turns out that if you try to attach RAG to it and evaluate its performance in instruction following, it's still not going to be good. And we can see that if we do the data analysis. So just like last time, this is LLM evaluation. And we also have an example of a statistical measure, in this case, ROGUE, which was discussed last time. But basically, it does sort of a text counting for this word in the original. How many of these words show up in the altered response? Calculation of how well these answers work, or it's a measure of how well summarization is done. So we only evaluate it on the summarization examples. So this is what our output looks like now. So this Colab notebook was used to generate LLM responses, and then those LLM responses were fed to to OpenAI, to ChatGPT, in order to evaluate those responses. So that's this LLM eval out of 10. We just modified it to be looking at the RAG responses rather than the fine-tuned responses. And here we're going to do the analysis of that data, which was then stored in the Astra table with the other results. Okay, so our first plot, RAG versus original response. Got some formatting stuff there. But basically you can see the RAG responses in general are equal to or lower than the original responses. And sometimes the original responses, especially when they're very good, RAG responses can't really compare. Because these original responses were generated by GPT 3.5 in the first place, Llama 2 is it's sort of on par, but it's a less capable model in general. You can sort of see the difference here. And then our next plot, on the left is our RAG response, on the right is our original response. In the original, this here, analysis, down. And this is the original comparison between the fine-tuned and the original, where it's, sort of at or above the original responses. But then in the fine-tuned, this is the fine-tuned response is both higher and less varied than our original responses. But if we go back to look at the RAG, we have a lower and more varied RAG response, especially more weighted downwards, because of those instances where it just straight up did not output an understandable response to the question.
Yeah, this just goes to show that data engineering, data cleaning is always a part of AI. It's always a part of
so there
generative
are
AI.
several places where we could theoretically have made a difference in this. If we were using an instruction fine-tuned Llama 2 in the first place, then one, our fine-tuning results would have been less dramatic, because it would have already, so the original responses would have been decent at following instructions, even if they didn't have any understanding of the Cassandra link articles that we fine-tuned with, or the technical understanding that sort of backs those. we could have changed the chunking of the original articles. Remember, they were chunked into sections of 8,000 characters because of Astra database limitations, but we then used those chunks, regardless of where they fell, in order to generate our embeddings. And then we could have changed the prompt. So our original prompt said follow the instruction, provided the instruction, provided one piece of context, and then prompted for an answer. Whereas the RAG one is the same format, provide the system prompt instruction, follow the following instruction, provide the instruction, provide the original piece of context, provide one piece of RAG context, provide two pieces of RAG context, provide three pieces of RAG context, prompt for response. So we could have mixed up that formula. Basically, there are several places for intervention, all of which will be at least a little bit necessary to get good results out of a RAG system. So you can't say connect your RAG system to GPT-2 and expect good results. And you can't, provide it with nonsensical or false data and expect factual results out necessarily. So we can see our original rating, 5.7, standard deviation of 1.9, became our RAG system with an average of 4.168, standard deviation of 2.15. And like I said, if we did human evaluation, we'd likely get even lower numbers because it produced something that a machine, GPT 3.5, might say is all right because there are, references to the original context in this result. So it can't be a 0, right? But if what comes out is mostly incomprehensible, all formatting tags that you have to scroll down to a certain amount to even see what the response is trying to give is, then a human might rate that a 0, whereas GPT 3.5 might say, I don't know, there's a little bit of information in here and rate that a 3 or 4. All right, so in terms of which questions it did well or badly on, so you can see our RAG responses are generally lower. So these are our RAG results. These are our original results, but it still provides generally decent results for number 10 style questions, which are for not the evaluation prompts, the instruction prompts. On summarizing the impact of an article, but you can see we're generally still scoring lower even than the original LLM. So we have lower scores, we have higher standard deviations. It's all in all a worse system. And then we can use Rogue and we get out similar results here. So Rogue, like I said, is the statistical measure dealing with words in the original and words in the response and how many of the former appear in the latter. And you can see that our original LLM, Llama 2, 0.28 or 0.129, and we got reduced scores for our RAG LLM. So RAG in general can be a powerful tool. Like for example, our RAG chatbot based on based on Astra documentation was fully able to answer questions about Cassandra or in Astra that were contained in its documents without any, based on user prompt, without any issues coming up. But that used GPT 3.5, used embeddings that were chunked upon like paragraph boundaries, just about. There are lots of these little things that have a large amount of influence on your RAG results. All right, I was also going to have a section where we would sort of prove this by taking in relevant context, building our prompt manually, and just putting that through GPT 3.5 and showing that, a RAG system built properly does get reasonable results even on this data, but we are at time.
We are, yeah. Let's spend just a moment and do the big picture comparison here, right?
Sure. So, sort of big picture, a base LLM has a lot of generalized knowledge, but has problems with factuality, and it can also have problems with, depending on sort of what level your model is at, whether it's been instruction fine-tuned, how good it is in general at predicting what the next letter, the next word that you want out of it is. You're going to get a lot of variance in how well it can do things like respond to instructions, write code, respond in particular formats, understand the meanings of particular words used in a specific context, all these things. Methods to fix some of these issues can go one of two ways. You can build a RAG chatbot where you worry about all these things, but you generally don't use a whole lot of compute power. The embedding model, once it's built, is relatively quick and painless. The retrieval is relatively quick and painless. You send it to the LLM the same as ever, but you can use whatever LLM you want with a RAG chatbot. You're not limited to one that you have the weights for and potentially are running locally on your machine. And fine tuning, you determine your goal, you build out a data set. It has to be a relatively large data set. You spend a lot of compute power doing the actual fine tuning on a GPU. You end up with a model that still might have problems with factuality, but definitely understands, at least as long as it was included in the training set, what types of questions should lead to what types of responses, which is something that you can't necessarily expect a RAG chatbot to understand no matter how well you build it out.
Obi, thank you so much for giving this talk. There aren't any additional questions in the chat here, and I think you've done a really great job clarifying these two LLM scenarios and giving us an evaluation about how RAG performed versus how fine-tuning performed. With that, I think we're going to close. Thank you, everyone, for being here and for listening, and we will see you next time. Okay, the stream has stopped, and the recording has stopped.